This is how we do. Okay. So actually, the first line is the developing the logistic regression model, and then you can do the summary. So I will show you this one. So this is the result. You can see the what is the estimation, what is the p-value. Then we can tell all of them are significant. And then this line x equals the predict the logistic regression data frame, and then you calculate the p using the px, right? Then you can actually calculate. So if you use this one, right? If you don't type in the response, yeah, you have to be careful because what this x means is the just the regression part here. So I will. So if I change it, I block out this one and then just using the predict, and then I didn't type in the like a response here. Then what it will return is the actually the, as you can see, x is this is minus 1.32239. Here x is, if you don't use a response, this x will be this x will be just that b0 plus b1 x1, only the regression, linear regression part. This will be this x. So if you wanna find out the actual the probability, then you have to calculate it this way. Then you can see that this minus this 21% is the probability of y equals 1, and this calculation is come from the e to the minus 1.322392 over 1 plus e to the minus 1.3223 is this number. Okay, but this is kind of tedious to find out. That's why we will use this formula. So I will block out here. We don't need it, but instead of that, so we can just use a predict and then add the option type response. Then you will get this is the 20 and 30 cases. So I will just change it to the 20, 30 cases. Right, 20, 30 cases, again, you can see that it's 21%. And also, you can predict the multiple cases. This is only one cases, but you can predict the multiple cases at once. Then you will see the two numbers here and here. And first one is the first case is a 2030 and or 3030. Right, this is how you do the logistic regression. To get the final answer will be slightly different than our LM case, but still we will use a predict function. Okay, that's why this if you don't have it, the output will be just only the linear regression part, not the exponential part. And odd and accurate rate. So what is odd? So in LPM, linear probability model, the BJ measure the partial effect of the XJ on the predictive probability. However, logistic model, so it's not straightforward. It's because we have to get through these exponential things, right? It implies a positive or negative relationship. It does not imply a unique partial effect of the xj on the predictive probability. Again, it will get through the whole complicated formula. So useful way to communicate the influence of the predict variable nonlinear case is to plot the simulated value, and you have to just try and how it happened. So you cannot directly tell what happened. You cannot simply increasing or decreasing. It's not easy because it has a it changed the denominator and also numerator together, so it's not clearly you can tell it's going up or going down. Okay, the objective outlined in the introductory case is detecting the spam. So this is actually the spam example. So estimate the linear and logistic regression. We can do the linear regression and logistic regression on two cases. Use simulation to highlight the partial effect of the. So here, what is the partial effect of a recipient? So you can put the recipient is like a 1, 2, many other different things, while holding the hyperlink and then characteristic fixed as a sample mean. So you can use just a hyperlink and then characteristic sample mean, so fix it as a mean, and then you just change the recipient from 1 to like 20, or I don't know the range, but you can try and calculate all the cases, then you can tell what actually happened when recipient increase, how much the probability of spam changes. So that's the only way you can tell, right? So you can run the regression with just linear probability models. This is just linear regression. So this is the p-value, right? P-value is in parentheses. So it's a p-value. So everything is statistically significant, but actually what you can see is a totally different number. And using simulation, I said 1, 2, 3, 4, 5, 6, but actually you can do the like a 10, 20, 30, 40, 50. And then if you're using the LPM, linear probability model, as you can see, this is increasing, and also logistic, this is also increasing. So you can tell as a recipient increase, your probability also increase. However, here, this difference will be same as this difference. Roughly 44 to 60 is about 16, right? 44 to 60, I will just roughly calculate 60, and then this is about 92. So this is a 16, this is a 16, and this is 16. However, in logistics, this is a total different. This is about 26, but here only 4 increase, right? It's a 40 to the 66 is about 26 increase, but here only 4 increases. So you cannot tell in linear model. You can tell one recipient increase by 10. One, actually you can tell what will happen. The number of recipient increase by 1. What will happen to the probability? However, logistics regression, then you cannot tell because the increment of every step. I mean, here increment is all same, but the result of the probability increasement is all different. Right? So if you draw the actual LPM and then logistic regression here, right? So maybe this is going this way. so that this becomes sigmoid function, and then this is a linear function. So you can tell what's the difference. Usually in general, this is not our example, but in general, you can have a linear function so that can go up or go below the zero. But logistic regression case is you can try to fit into the sigmoid function so that any prediction will not go above 1 or below 0. Okay, what is odd? Odd is actually this calculation. Odd is a probability divided by 1 minus probability. So this probability 1 minus p is the this is a probability of success, right? Probability of success over probability of failure. This is what we call this odd. That's why the calculation is like this. 1 minus p is if the p is a probability of success, 1 minus p is a probability of failure. So this calculation is odd. And this odd is widely used in the gambling, right? Popular in the gambling and sports. So you might have seen like a World Cup. Then you heard that what is the odd? Actually, they don't call it a probability. We use like odd. What is the odd of the certain team will win against another team? That's why they use odd rather than the just simple probability. So why we bring this odd to here? Here why we use why we can use odd is a transformation from the probability to the odd, and the odd is a monotonic. Monotonic means it's a p has increase, implying that the one increase and that the other one increase too. So probability and also why we care about this odd, why we bring it to the logistic regression is because of that. If we use a probability p here, and 1 minus p will be write down like this, right? And then this 1 will change to the 1 plus e exponential things, right? 1 plus exponential things minus this is 1 plus exponential. Here are the e exponential, right? So this one, this and this will be cancelled out. So it will be just simply this one. So if you divide p with a 1 minus p, this is a 1 minus p, then what will happen is this one will be cancelled out. The denominator will be disappeared, and the only thing you can have is this one. Now, if you apply the log on both sides, log of odd will be just simply linear regression. So that's how we bring the odd to make it easier to run the regression, linear regression. So inside of the logistic regression algorithm, there is that include a linear regression model. So if we use odd rather than the probability directly, this one will become a pretty simple calculation. That's why we use odd here. So here you can tell what is the coefficient b1 or b2, b3 is approximate percentage change in odd, not in probability. Okay, so you can tell because this is a log, so you can tell what is the percentage change when the x variable increase, then b1 times 100 will be the percentage change in odd, not in probability.